Isaac Asimov once said that great scientific breakthroughs are not heralded by a scientist leaping up from their workbench and shouting Eureka. They're heralded by a scientist poring over their data saying, that's weird. By that definition, cluster headaches should be poised for a breakthrough because when you pull the camera back and look at them from the outside, they're kind of a weird disorder. They're one of the most intense pains known to humanity, with attacks that occur just because it was time for an attack. And after 15 to 180 minutes, the pain vanishes as rapidly and mysteriously as it came on. They're an intense pain that feels exteroceptive, like an attack from the outside. And patients not uncommonly respond by attacking themselves, hitting their head against a wall or striking their head with their hands. When you think of other types of intense exteroceptive pain, like complex regional pain syndrome, striking a part of the body that already feels injured, that's already in pain, is the last thing a patient would do. It's an intense pain. It feels like an attack, and it causes agitation, and heart rate slows down, the exact opposite of fight or flight. So there are many aspects of cluster headache that are paradoxical, mysterious, and strange. It seems entirely fitting, then, that one of the streams of research currently for preventing cluster headaches focuses on the psychedelics, a class of medications best known for their capacity to distort reality. That seems fitting, because on this plane of reality, cluster headaches do not seem to make a lot of sense. What I hope to demonstrate in the attached article, however, is that everything that seems mysterious and inexplicable about cluster headaches actually makes perfect sense and is straightforward to explain, provided we make a single assumption, an assumption for which there is some empirical support. That in 1983, Lee Kudrow was right when he said that cluster headaches are an overly zealous response to hypoxia. In the article, we'll see that some of the anatomical structures implicated in cluster headache, namely the paraventricular nucleus of the hypothalamus, the solitary tract nucleus, and the communication between the two, has also been implicated as part of the response network to hypoxia. We'll see that the neuropeptides whose levels rise during a cluster headache attack, CGRP, PACAP38, and vasoactive intestinal peptide, also seem to play a role in hypoxia detection and response. In particular, PACAP38 is found in the carotid bodies that detect hypoxia. It is required for normal ventilation, and its levels rise in response to hypoxia just as they rise in response or as part of a cluster headache attack. Vasoactive intestinal peptide, whose levels rise during a cluster headache attack and whose levels correlate with the severity of cranial autonomic symptoms during the attack. Vasoactive intestinal peptide terminates hypoxic signaling, presumably so that the body and cells can make maximum use of the oxygen as it's restored. I know of no explanation for the self-limiting nature of a cluster headache attack, but I can say that the response to hypoxia is self-limiting if it involves release of vasoactive intestinal peptide, and vasoactive intestinal peptide is indeed released during a cluster headache attack. We'll also see that the trace amines, tryptamine and tyramine, that are normally present in very small amounts in the brain, but whose levels rise during a cluster headache attack, we'll see that that increase in trace amines can be thought of as a neurochemical signature of hypoxic conditions. We'll also see that for each of the genes that have been implicated in cluster headache in genome-wide association studies, provided the functioning of the gene is known, each of those genes also plausibly has a role in hypoxia signaling, communication, and/or sensitization, overlapping genes. Clinically, We'll see that the times of day when a cluster headache is most likely to occur is also the time of day when relative hypoxic conditions are most likely to occur in the bloodstream. We'll see that the times of year when cluster bouts are most likely to occur are times when the hypoxia system is most likely to be stressed, either because the absolute amount of oxygen in the air is lower because atmospheric pressure is lower, or that the absolute amount of oxygen in the air is varying the most from day to day, or that the hypoxia system is being sensitized by thermal stress because the hypoxia system responds when we're overheated or under cold conditions. The fact that smoking is a risk factor for cluster headaches is less surprising when we realize that smoking is a way of sensitizing the carotid bodies to the detection of hypoxia. In particular, nicotine sensitizes to the detection of hypoxia, and smoking is also associated with an increase in succinate levels and levels of reactive oxygen species, and both of those are signaling molecules, classes of signaling molecules for hypoxia. The fact that nitroglycerin is a trigger is less surprising when we realize that nitroglycerin stabilizes hypoxia-inducible factor and therefore prolongs hypoxic signaling. Alcohol as a trigger is less surprising when we realize that its detoxification in part is through cytochrome P450 2E1, and that enzyme system consumes oxygen, so that the detoxification of alcohol causes a relative depletion of oxygen. The slowing of heart rate is less surprising when we fit that into the context of other oxygen-conserving reflexes. And in particular, the slowing of heart rate is thought to be a way of protecting the heart during low oxygen conditions. The fact that cluster headaches currently are twice as common in men than women, and historically 4 to 5 times more common in men, fits with the sexually dimorphic nature of hypoxic detection. In particular, progesterone may protect against low oxygen conditions. And the agitation so characteristic of a cluster headache attack that is so unusual as a response to pain is not at all unusual, and in fact is prototypical for the response to being suffocated, the response to low oxygen conditions. And so the neuroanatomical, the neurochemical, the genetic, and the clinical features of cluster headache make a great deal more sense when they're fitted into a framework of hypoxia detection, communication, and sensitization. This is not just of theoretical significance. There are medications, nutrients, supplements, breathing exercises, and lifestyle modifications that we know impact the hypoxia detection system and that can desensitize to hypoxia, can make a sensitized hypoxia system less sensitive. Whether any of these would be safe and appropriate for cluster headache, we don't know. But I think those are very appropriate areas for research because in the ideal, it might turn out through research that we're able to repurpose molecules that are available currently and behaviors that are available, of course, currently, repurpose them for the prevention of cluster headache. None of this constitutes a proof. We do not know whether the hypoxia theory is correct. That will require clinical trials and advanced neuroimaging combined with cluster headaches and pharmacological probes for hypoxia. What we can say at this point is simply we have an elaborate and, I hope, convincing plausibility argument for the hypoxia theory for cluster headaches. But I think the cluster headache theory, the hypoxia theory has tremendous heuristic value as a way of guiding future research. In 1983, 42 years ago, Lee Kudrow opened a door for us. We have yet to walk through that door, but I think we should, because on the other side of that door, we'll be able to ask and answer questions about cluster headache that we can't imagine currently. We may even be able to find a cure. I don't know. I do know this, though. On the other side of that door, things are a lot less weird than they are on this side. Thank you. I hope you enjoyed the article.